Okay, in this video I want to make a little bit more of a connection between hybridization and the VSEPR model for the shapes of molecules. I sort of talked about them parallel to each other. So I talked about hybridization, when it happens and why it happens and what shapes the molecules take on, and I talked about the shapes of the hybrid orbitals, or at least the first few. And then at a different time I talked about how to use the VSEPR theory, but I never really put the two things together to show that they are complementary to one another. To do that, I'm going to focus on three molecules that all have the sp3 hybridization. And I'm picking that because it's one of the more common hybridizations, and because these are three molecules that we work with really regularly, so we should explore these in a little bit more detail. Now, when I say sp3, what that means then is that I have 4 sites where electrons exist. So when I look at this list and I compare it to this, I'm going to be looking at these 3 VSEPR shapes. These VSEPR shapes are all the sp3 VSEPR shapes. There's 4 different spots where the electrons are. So let's start with CH4. To do the hybridization for CH4, I'm going to start with the energy level diagram for carbon. So I have my 1s2, my 2s2, and my 2p, what could be 6, but here I'm only going to have 2 electrons available in it. Now we can see from the Lewis structure that carbon wants to form 4 bonds. And so, to hybridize, it's going to promote 1 electron up to that p shell, and then all the shells, which have to be identical, will hybridize into sp3 shells, each containing 1 electron, being available to form covalent bonds with 4 hydrogen atoms. Now we know that the sp3 is the tetrahedral shape, and we'll see that that corresponds to the tetrahedral shape of CH4 with a bond angle of 109.5. So sp3 is one of these 3 shapes. In this case it's the tetrahedral, and we can see if we put a bond on each end, then the overall molecule has that tetrahedral shape. 109.5 is the normal bond angle for a tetrahedron, and so VSEPR, we're going to see, slightly corrects bond angles to allow for to recognize the fact that lone electron pairs will repel a little bit more than bonded pairs. So in this case, we don't have any bonded pairs, so we're going to just get the normal tetrahedral angle of 109.5. In our future examples here, we will have lone electron pairs, and then we'll see that we are getting slightly different shapes, or slightly different angles. So here's our NH3. We know from previous that it has a triangular pyramidal shape. From a energy level diagram standpoint, our nitrogen looked like this. It wanted to form 3 bonds. You might be mistaken and think that it would just use these 3 P's, but it doesn't. It hybridizes in that lone electron pair in that same level. So my 2 S's and my 2 P's change into sp3, and there, that represents the lone electron pair, and here are the 3 shells available to make the 3 bonds with hydrogen. Now, the sp3 we say has a tetrahedral shape. And when we say that, what we mean is if we imagine all of the orbits associated with where these electrons are, it forms a tetrahedron, just like with methane. However, in this case, since one of these is occupied by a lone electron pair, the overall shape of the molecule doesn't actually end up being a tetrahedron, but if I look at the molecule itself, it ends up being a triangular-based prism, which is why VSEPR calls this trigonal planar. In fact, if we look at these shapes, and we recognize that this shape and this shape are essentially the same, just with this atom removed, we can see that having this lone electron pair, the hybridized orbitals are in the same shape, they just are missing their top hydrogen, and they're missing something up here, And so instead of looking tetrahedral, it looks trigonal planar. Now remember that VSEPR corrects these bond angles a little bit. So if that one's 109.5, this one, due to the increased repulsion from that lone electron pair, is reduced to 107. So we still have an sp3 hybridization. From a hybridized shape or an orbital shape, it's still tetrahedral. But when we consider where the actual atoms are associated with this molecule, recognizing that there are none on the lone electron pair in the top, we see that we get a resulting trigonal planar shape for NH3. Water is just going to go a step further. Instead of having one lone electron pair, it's going to have two lone electron pairs. So we're used to seeing the Lewis structure of water by now. From an energy level diagram perspective, without bonding, it looks like this. You might think the two hydrogens hop on here, but again, like I said, with this, hybridization includes all of the electron pairs as well as the bonded pairs. So here, we go for an sp3 hybridization. Keep a note, the hybridization does not include inner shells. So those 1s's we don't need to worry about. Anyway, here we have our 4 sp3 orbits, 2 of which contain lone electron pairs and 2 of which are available for bonding. The shape of the orbits is tetrahedral. So if I imagine my oxygen molecule, I have tetrahedral shape to my actual orbits, but 2 of them are full of lone electron pairs, and only 2 of them form bonds with our hydrogen. So what we end up seeing is this overall angular or bent shape. So that's why when we consider where the actual atoms are, we don't call this tetrahedral anymore, but we call it angular. Once again, the lone electron pairs result in a higher degree of electron-electron repulsion, and so this angle is dropped down to 104.5 now. And we can see that the VSEPR shapes are telling us the shape of the overall molecule, taking into account where there are atoms and where there are not atoms, versus the hybridization, which is telling us the shape of the orbits regardless of whether or not they have atoms bonding on the end of them. So all of these have tetrahedral orbits, and then when we consider where the actual atoms are, we can see that we can give them different names based on what the overall molecule looks like. Keeping that in mind, we can go back and recognize then that some of these are sp2s, and there's some that are even sps, and then there are bigger things where we have, if we have the 5s, we have some special hybridizations we haven't talked about yet, sp3d, and the 6s we can even go to sp3d2 or even sp3d3 for these guys. So most molecules fall in this range, but I'm going to do another video, I think, where I look at some sp3d or sp3d2 molecules, and we'll see how that all corresponds with shapes and Lewis structures. But the main ones we have here, we have our sp3, which is tetrahedral, and then we can break it into these 3 things. We have our sp2, which is trigonal planar, which can once again be broken into those 2 things based on whether or not there's actually atoms at the end of those orbits, and finally sp, which is linear. So that's how hybridization and VSEPR are related to each other. Again, the VSEPR is a little bit of a slight correction, and it has a nice easy system to use to determine the shape. But in the end, when we're starting to think about why they take on those shapes, we should really be thinking back to the shape of the hybridized orbitals.